Hi, everybody, and good afternoon, and welcome to our weekly Hurricane HQ&A system session. We're live again this week on YouTube and Facebook and TikTok and X and Instagram and LinkedIn. And if you know anybody that's interested in AI and interested in hurricanes and interested in the latest technology and weather forecasting, this is the session for them. Text them right now and tell them to get on their YouTube or their Facebook or whatever they want, or their TikTok, whatever they want to get on, because they're going to enjoy this session, because we're going to talk about what I think is the newest and most kind of amazing and surprising thing to come out of this hurricane season. As weird as it's been weather-wise, it is fabulous how the new AI models, and in particular, the Google DeepMind AI model, has come to the fore this year at the Hurricane Center using it. And of course, we look at it at Fox Weather, and pretty much everybody is looking at it now. And I have to disclose that I was had a little advisory role in the beginning of this early in the spring, and I want to put the emphasis on little there, because I certainly didn't do any of the heavy lifting. That was all done by the Google DeepMind scientists. And we are so pleased to have with us this afternoon a research scientist and key person in the development of this amazing project. Ferran Alet is with us. Ferran, thanks so much for coming on and being willing to take questions from the audience this afternoon. Thank you.
No, thanks a lot for inviting me. I've been watching your forecast and analysis this season, and also it's been wonderful to collaborate with you on how to better present our models.
Yeah, it's been a great project, and it's just to see the progress. I mean, in the beginning, I thought, okay, it's another AI model, although we had a little preview of it, and we knew it was going to be pretty good, right? Because it ran, you ran old storms on it, storms from previous years. Well, let me just ask you, is it better than you thought it was going to be, or did you just have confidence that, all right, you figured something out here with the way you have implemented the AI in your special case, and it was going to be great?
Yeah, that's a good question. So on tracks, we knew it was going to do well because we had been researching it for about a year, and mostly since January 2024, and it was already giving very good weather prediction and track prediction results. And so the climb has been more gradual there, so doing pretty well since the beginning. Whereas in intensity, there was like a few months where the climb was astronomical, and so we were very positively surprised.
Well, and this hurricane season has been, I don't know, has it been unusually difficult when you compare it to, do you have any sense of that? I mean, this is your first real season seeing it in action in real time, right? But
yeah,
the storms, the past storms you've run, is this season as weird as it feels like to those of us experiencing it in real time?
So we are mostly waiting until the end of the season, at least on our front, to see a kind of a very thorough analysis on it. Because we, in our case, we kind of are scientists and are trying to collect like sufficient evidence to then make a statement. So for instance, and also, so mostly we are like from what we've been seeing, it does mostly align with our past analysis on 23, 24, but we haven't kind of look too much at 2025. We can go more into it if you want, but we like in ML, you don't want to look at your test data too much.
Right.
So we're trying not
While you're doing it. Let me say, by the way, if you have a question, and I should have said this before, but if you have a question and that you want us to address related to the AI, Google DeepMind, or just weather, anything you want to send in is fine. If you would put a Q colon in front of it, it'll help Jordan Overton, who is at New York headquarters and screening your questions and organizing things for us. He's running the system there to put all this together and stream it out to you. So anyway, that'll help Jordan organize it so that we can see the questions efficiently. So let's take a look at what's going on out there right now, including we'll talk about the Google DeepMind model performance on this last system, Imelda. So here you see what has happened to Imelda there. It's getting all stretched out in the North Atlantic. It's now had its last advisory as of 11 a.m. Eastern time today. Still a 75-mile-an-hour system, so this is a powerful system. As a matter of fact, it's heading for Scotland, I guess, as Storm Amy, they're calling it there, and the final advisory issued by the National Hurricane Center. Now, I'm going to run the Google model as it forecast when it was approaching or going to approach the southeast coast. So this is back last Thursday. So this is back on the 25th. And I'm going to just run through, and then we're going to go back and understand it a little bit step by step, okay? So because I want to show all the other stuff going on out there. But here you can see that the question was, is it going here or is it going here? And a bunch of models had this bifurcation one way or the other way. But the red is what is the mean or the average of these 50 lines. And notice that it said, no, odds are based on this information, which nothing is simple, but based on this information, it's going offshore. And we have, appreciated that kind of heads up but still, you have to say there was a possibility of it going there. And I'm going to ask Ferran about the details of this in a second. But just watch this now as it goes through the days here. And you can see that it danced around a little bit, but the commitment was for the mean to offshore. And so the mean is like the forecast of, days gone by when we used to look at a deterministic forecast. So it's just a different world here. Anyway, we'll talk to Ferran about that in just 1 second. Okay, so let's look at what is happening in the U.S. at the moment. And the big thing right now is the issue in the ocean all the way from just south of New York City all the way down to the Palm Beaches and even to some degree in Miami-Dade and Broward County in South Florida, because we have the energy here from Imelda, and what this white area is up here is from Umberto, both of which now have gotten involved with the front and transitioned into non-tropical systems, but they're essentially energy is emanating from them in the entire Atlantic basin. And so this has just put all this extra, these strong swells coming toward the coast, and we end up with big waves eroding the beaches. Have you seen the incredible pictures coming out of North Carolina? I think there's 7 homes that have been washed into the ocean now from this. And this is going to continue. So look in the upper left there, that's the time here. And watch as we go forward in time. The storms go toward Europe, but there's still energy in the water. Now it's less as we get to Saturday, especially in the north. But what's happened is behind the hurricanes, high pressure is building in, and then we get a circulation like this and just relentless wind pushing the ocean water at the coast. So elevated oceans, dangerous currents all along the Atlantic coast, especially south of Cape Hatteras. And it looks like by the weekend, a little less in Cape Hatteras. Finally, they'll get some relief, but it's not really over even by late on Saturday. And then look at the satellite picture of that same area of this time. Look, you can see Imelda up here, and there's this front now kind of extending out of it, and high pressure is pushing in, just surging in behind what was the hurricane. And that high pressure is what's pushing the water here. You can see these clouds here. These clouds are caused by cold air over top of the warm ocean water. And in parts of the eastern part of the US, you can feel that cool water. But when we get down here, the bottom where that front kind of meets Florida, you can see what's happening with the wind flow here. Remember, we have the wind coming in like this north of it, while south of it, the wind is coming like this. So, we could get a circulation developing in there. The odds are not high because the upper level flow is not really conducive, but there's a maybe there. So we'll just keep our eye out for that. And as a matter of fact, the National Hurricane Center has a 10% chance of that developing over the Bahamas and lifting north or northwest. Like I said, the upper level winds don't really look conducive, and there's a decent chance if it does develop, it'll be a non-tropical system that it will move over Florida. And so it's kind of a low odds thing. A little higher odds out here, but only 20%. And we can see this on our tropical threat graphic. Now, I don't know if you've seen this, Farhan, but what we do is we take what are called the ensemble members of the European, the GFS, and the Google AI model. So that makes 130 members or so. And then we look for essentially the density where all those models agree there could be the development. And so you can see in this area here where the Hurricane Center was highlighting at 20%, well, the blues are in the low range here. So we're all sort of in agreement there. And way down here, this is only in the less than 10% range here, according to the analysis that we do there with the three models. And we show some possibility of development over here. The Hurricane Center isn't picking up, but the odds favor actually that happening in the Pacific more than in the Atlantic, which is just some random possibilities there end up showing that. So anyway, that's where that stands. And this is the Google AI ensemble members, they're called, for that system out there. And if we count these, so the way this works is you go in and you actually count the lines. So let's just count the lines for one moment here. And okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. So it looks like maybe 14 lines. And there are 50 members. So divide that out and you get something less than 30%, right? Am I doing that right, Farhan? That's the technique?
Yeah, exactly.
Okay. So, all right. So let's stop there for a second. And I want to talk about this new way of looking at computer models. I mean, for those of us that have been doing this for a long time, and I'm sure a lot of people in the audience, we looked at the European or the GFS online, a deterministic model. Not that we didn't know that ensembles, the idea of taking one model and changing the initial conditions and running it again and again and seeing what kind of a fan of possibilities you get. Obviously, we've been looking at that idea for a long time, but I think that maybe last year or this year, it's really shifted to where the ensemble approach, which is also your approach, is the way to do it, is to run these models and then look for an average of those possibilities and use that as the deterministic forecast. Is that a shift in philosophy as far as you know? And is it really because we have the computer power to do it? Now we can do it this way and it is fundamentally better?
Yeah, I think that's probably one of the key reasons why, at least in the NWP world, and then in the AI world, one of the advantages of the AI models is that they can run much faster. So it used to take like a supercomputer multiple hours to run a forecast, and now in AI you do it in kind of, let's say, like a big but still like personal size computer in about a minute to generate one of these forecasts. So we just spin out like maybe 16 computers to just make this forecast in about 10 minutes.
Wow. And you're talking about you're talking about running the model around the world, right? For multiple
Yeah,
cyclones.
yeah, yeah.
Yeah.
In our case, the model is global,
Mhm.
so it predicts kind of the weather everywhere around the world, and in particular also cyclones everywhere around the world. And so, yeah, we just predict 50 possible futures.
So let's go back to this thing I was just showing here that we're talking about. So just to be sure that everybody understands it, because everybody can look at this stuff online, there are 50 possible, and here we're seeing about 14. So you literally, if you want to know what the odds of the system developing a circulation, which is all we're talking about from an odds standpoint here, right? You take the 14, divide by 50, and you end up with whatever percentage you end up with, and that's what the model is saying the odds of that happening. Is that the right description?
Yeah, exactly. So you simply multiply by 2 and you get the percent
Right.
probability. So in this case, 28%. So
28%.
it's,
All right. So now we showed, in fact, we can look at it again here. Let me hang on just a second. It'll go. Oh, well, there's the tropical threat analysis. But okay, so going back to this one, and we showed that this one has, go ahead and plot the average or the mean. But on the system that hasn't developed yet, you don't do that. Is that because there isn't a good starting point, or what's the
ah,
difference between a system that doesn't have, that thing it hasn't even really come off Africa to where we know what it is yet. This is a sort of future development kind of system. So what's the fundamental difference there?
right. That's a good question. So before the cyclone kind of exists, we don't have a time equals zero prediction onto which to what we call pair all the different ensemble members. So it's hard to kind of maybe as a human maybe it's easy, but for a computer model it's there's not objective way to say, oh, this member and this member should be the same cyclone versus, oh no, they should be two different cyclones.
Mm-hmm.
And so we wait until the cyclone exists at present to say, okay, now we know which cyclones that we were predicting are actually cyclone Imelda or this particular disturbance. And so that's why we mostly wait for you, but like for the cyclone to exist. But we also give so we have a tool called Weather Lab to visualize these cyclone models,
Right.
and we allow the user to group a category of cyclones and then treat them as a single group, and then you can compute the mean and so on. So it's not like it's incorrect per se to consider these groups, but it's not fully well defined, and that's why we prefer not to do it and let the user choose if they want to do it.
Yeah, and it's especially nasty problem if you have two cyclones near each other, I guess.
Exactly.
Yeah, so
Exactly.
if you go on, anybody that's used Weather Lab, the Google DeepMind site for this, you can just Google it, Google Weather Lab, and you'll find it. In the top toolbar, you'll see a tool that allows you to draw a box around the dots that are out there in I draw a box around the dots is how they start out, each one being a different ensemble member, and then it'll show you what, if that is the group that goes with that storm or that system, it'll show you what the average of those dots is. But it's because it hasn't developed, and I guess you don't really wait for it to be a cyclone technically, because a cyclone is supposed to be a closed circulation, right? Invest, if the National Hurricane Center designates
Right.
it an invest, doesn't that trigger
Yeah,
you say that's
exactly.
enough?
Yeah, we basically wait for them to tell us, oh, there is something here.
Hmm.
Even though we might predict that there's going to be something in the future, we wait for them to kind of tell us, okay, now that's what's going on at present time. And then once we have an official confirmation there's something there, then we start to track it.
Yeah. Okay. So just one more thing, and then we're going to get to your questions. Let's go back and look at that map once again of Imelda. This is when Imelda was just getting started here, so this was really not much of a system. So what do we make of these? Is this should we just think of this as at this early stage in the system? We should be aware of the possibility of this system coming ashore in the southeast, but maybe it's a little more likely to turn. How would a user interpret what we're looking at right there.
Yeah, so a bit similar to what we did like a few minutes ago, in the sense that I would potentially count, okay, how many scenarios out of the 50 that we predict make landfall, and how many don't make landfall. So in this case, maybe it was slightly less than 50% of the cases that were making landfall. And the other thing that's interesting is that the model really can show uncertainty very visually. No, so it starts being quite focused and saying, oh, we are really pretty certain that that's where the cyclone is going to go, even before the cyclone kind of pops up and makes cyclogenesis. And then there is a moment that it starts to be quite uncertain. And so because we show all the possible futures, you can really visually see the uncertainty there.
And we're looking out. In this case, we set these to normally 7 days. So 7 days ahead on a system that has barely developed is always going to have some level of uncertainty. All right. So just stepping through them, you can see. I mean, this is just the odds of the way the cards are dealt, right? I mean, when you have just a very uncertain scenario, the fact that it jumps around a little bit, I mean, you expect it to do that, right? I mean, is it?
Yeah, and then
That's it.
That's what you want. So we want our system to be calibrated. We want to say that when there is a 20% chance of something happening, that there's actually a 20% chance of that. You never want to be too certain in either direction.
Right. So and let me use this to talk about one more point, and that is that the starting point here, and here, like here, the track it's very, very tight, right?
Yeah.
So I mean, again, I'm just trying to understand exactly how to interpret this well. So like we can say that that's high confidence there. Like, okay, we don't have to worry about Miami in this case,
Right.
and then the confidence decreases up here. Although by this time on Saturday morning, we were highly confident that it wasn't coming to the southeast. That's fair?
Exactly. Yes. So with respect to the track center, we knew it was not going to go to Miami. So kind of the let's call it cone, basically says that it's very unlikely that you'll go outside the yellow region. That doesn't mean that the effects of the cyclone will not have an impact,
Right.
but at least for the center, we were pretty confident at the very beginning.
All right, and just one more thing that I know my meteorologist friends would appreciate, because I just kind of figured it out, I think. And so tell me if I figured it out right. And that is that in your case, you start with the initial set of observations, and then you run essentially 50 different models, right? Each
Yeah.
model is a little bit different. Is that fair?
Mostly fair, yes.
Yeah.
So
Yeah.
so yeah, under the hood, we literally trained 4 models under the hood, kind of.
Oh, that's right.
With
4, and each one was
4 different models, and
that's
then
right.
so they all have seen the same data, but in different ways. So those models are already different, and then we inject some noise into the parameters of the network that basically make it slightly different for every model. And so yes, basically it's a collection of let's say 50 different models that each very similar but slightly different.
Right, and the noise that you put in is to make it somewhat random, right? To make
Yeah,
the
exactly.
are somewhat random, right? It's to simulate the initial errors.
Yeah.
Where the difference between that system and the way, since the European or any other numerical modeling system works, is they like change the initial conditions and run the same model, right? Is that and
Yeah, I think
where
they
you're modifying the model with
yeah.
noise, so it's a little different way of generating the 50 lines. Is that fair?
Yeah, I think yes, exactly. I think they might also modify some uh, physics parameters from time to time, but most of their uncertainty comes from the uncertainty in the data simulation. That's also why, for
Right.
instance, if you look at a numerical model like ENS, they start quite uncertain at the beginning, whereas we start quite certain at the very beginning. Usually they start maybe a bit too uncertain, and we start a bit too certain.
Yeah. Right, right. Okay. So anyway, when you're looking at the ensembles, you'll see the EN from the European Center. There's a kind of a big blob at the beginning of them because they say, well, we're not exactly sure of all these parameters, where in this case, it starts in one point and then the noise or the uncertainty gets injected into the models as they run. Okay, Jordan, let's see what folks are asking this afternoon.
Yeah, so our first question for this is from James. He said, a thing I have loved about his, albeit now limited knowledge, use of DeepMind, it doesn't kick up ghost storms. So, obviously, in the world of social media, there's a lot of people posting deterministic model runs that show major hurricanes striking the U.S. 384 hours. Not the case for the DeepMind.
Do you evaluate that? I mean, I'm sure you evaluate
Yes.
everything, but you evaluate whether uh, if like generally if you go way out in the future, you see lows popping up here and there and some random tracks.
Yeah.
What do you think about those kinds of things that pop up?
So two interesting things on that front. The first one is the evaluation that we do make. We have an evaluation that basically says that, as we were saying before, that if you say there is like a 10% chance of a storm being there, the 10% is actually correct,
Hmm.
and so that people can make the right decisions accounting for this probability.
Hmm.
We did observe that we predicted less storms than other models, and so we reached out to NHC, with whom we've been very closely talking this cyclone season, and we told them, "Hey, are you happy with the storms that we're predicting?" We knew we were calibrated, but we didn't know, for instance, whether they would want this type of ghost storms to be kind of aware that we knew about them, and they told us, "No, that's fine. What you're doing is the right level." So we kept it.
Yeah. Yeah. And, it's a really tough thing, right? Because what do you do when there's a 10% chance of a significant storm hitting? What do you do with that information if you're an emergency manager or if you just live there, right?
Yeah.
So it's the old question of when you start talking about stuff. I mean, on my side of the business, that's always an issue. Is like this system down in the main development region coming off of Africa. There are some models that show a significant storm that could affect the islands in a week, but very low odds of it being that. Most of the possibilities of affecting the islands are not a very strong storm when we look at the odds, not
Yeah.
when we look at necessarily a absolute deterministic model. When we just look
Right.
at the odds using this, you end up with low odds. So I mean, do you just tell the story with a smile, or what do you do? From a communication standpoint, this is something we have to learn, right? We have to learn to understand that what we do with low odds, high consequences events that are well into the future. That there's plenty of time to react to. So, anyway, it is one of the challenges. All right, Jordan.
Our next question coming in from Shane Brown. Are there plans to publicly provide additional meteorological variables from the FNV3, thanking pressure, UV wind fields, QPF, all as ensemble means?
Yeah, well, Shane knows all about this. So, all right,
Mm-hmm.
really good question, Shane. Ron?
Yeah, I think we'll put them out in the near future. We still have to see in what shape or form we put them out. It's likely that we'll first talk with hurricane agencies like the NHC and make them available to them first in some way. But it's quite likely that the base model that generating all these cyclone predictions under the hood is also making weather predictions, and
Mhm.
so we will also make them available in some form. We're still deciding exactly how.
Yeah, I mean the point is it's not just superficially somehow visually looking at the storm. So I've heard before this season actually it was, oh yeah, but the AI is just it's pattern matching. If it's never happened before, it's not going to see it. But we know now that that's not true,
Right.
right? Can you explain why that's not true? What's the box doing that is somehow figuring out stuff and figuring out that something is happening even if it hasn't seen it before?
Right. That's a good question. The bottom line is that we have lots and lots of data. So we're training on about 40 to even more years of data, and the data is quite high quality thanks to uh, contributions like the European Meteorological Agency making available reanalysis data that's very high quality.
Yeah, the
And so,
ERA5 data.
yeah, exactly, the ERA
Yeah.
5 data
Hmm.
set. And so even though there's not that many cyclones, I mean, there's probably too many, but not enough for a neural network to learn. There is really a lot of data for neural networks to learn about the laws of physics that govern the weather. And that's why our model can kind of learn these basic patterns of regular weather. And then we co-train the model to be good at this general weather with the cyclone data to then really understand how these cyclones that are really quite extraordinary, but then still follow the laws of physics at the end of the day. And then that's how it can generalize to predict hurricanes.
So you said you were pleased with intensity forecasts this year. Is that because you're putting high resolution data in? Is that what's turned that corner to make it be responsive to the intensity? Because intensity forecasting has been the challenge for all models, right?
Yeah, exactly. I think the co-training of regular weather with hurricane data that kind of is more high resolution has enabled the model to really understand the physics of the cyclone model. Even though the model is global and you usually need a regional model to be good at intensity predictions, we've seen that the machine learning can figure out all these patterns, and so we are pretty pleased with how the performance is going.
But there is a black box aspect to this, right? I mean, there is a mysterious component. Or is that true? That I mean, you're still a little surprised by you put this stuff in and you have some adjustments of weights and so forth, and amazing things come out the other side. Is how amazing is it to you at this point? I don't know. I don't know. It's amazing to me.
Yeah. There is a bit of kind of magic into how these models really can learn from these patterns and generalize in these amazing ways. Because at the end of the day, it's like meteorology is a field with decades of research, and so it's amazing for an AI to be able to learn all these patterns. At the same time, we do have some form of guarantees. From regular statistics, doesn't need to be neural networks, that you can say, okay, if it did well enough in the last 2 years and there's like 100 different cyclones in the last 2 years, you do have some confidence that maybe one cyclone it will not do well, but on average, it will do well. So you can have some certainty despite not understanding exactly how it's making predictions.
Yeah, it's it is a new world. Okay, Jordan.
Our next question coming in, you guys were just talking about intensity. We're going to have to break this one down a little bit, but we'll do it together here. So when using the intensity model distribution breakdown within the storm-generated tracks option, could we get an update that would allow location of ensemble members at chosen times within the intensity distribution option?
I see.
So interpret the question there, Ferran. If you
I understand the question correctly, it's like, where are the category 3 cyclones going, if I understand the question. So right now, there is not a way to sub-select by category. However, one of the things that we enabled since the beginning of the season, like after the beginning of the season, in part through feedback by NHC forecasters and Bryan, was to color the cyclones in Weather Lab to show the intensity. Because, for instance, Bryan, I remember you sent us an email saying, hey, really, the intensity is quite correlated with location. And I think you sent us an email.
Or with track, yeah.
Or the track, I think, close to Mexico, it had an intensity. Far from Mexico, it had another intensity. And so because the model makes 50 realistic futures, it doesn't make 2 different distributions. It really gives you 50 different scenarios. You can see the correlations between intensity and location, which is quite interesting.
Yeah. So here's a little trick. If you look at the storm and where you can display the intensity box in the upper right. And then if you put your mouse on, like in category, say it goes up to category 4. If you put your mouse on the track in category 4, it'll light up one of the members in the track, and that lets you know which one is category 4. And you can kind of go through it that way and select them one at a time if they're separated enough. Anyway, if you try that, you can kind of get the idea of what you're trying to do, I think, but you actually don't want to be selecting the members here. You want to be selecting the members up in the intensity box. I think that'll work for you. That makes sense?
Yeah,
Seems like
exactly.
a good idea. Okay.
Yeah,
All
that's a
right,
good
Jordan.
idea.
All right, Jordan.
All right, your next question coming in kind of along those lines. You just talked about upgrades. James asked, what, if any, upgrades to Google DeepMind could we anticipate for next hurricane season?
All right, Ron, what's the future going to yield here?
Yeah, that's a good question.
Mhm.
I think we'll keep improving the model, so we should be able to get uh, still better tracks and better intensities. Another thing that we're looking forward is we were talking about the efficiency of generating these machine learning models, and really the last one, this FNV3 and future models are even fast compared to other machine learning models. So they're really quite efficient. So that enables us to make many more predictions than even previous machine learning methods. So we're looking forward to expanding the number of ensemble members, probably around 500 or even more. And so that could enable regional agencies or human experts to look at low probability events, as well as to better estimate probabilities like this 20%. Instead of having 50 members, if you had 500 or even 1,000 members, we could really start to see really very good estimates of probabilities, as well as correlations, right? You could start to talk about, okay, if a hurricane is going to Miami, what's the distribution of the category that pass near Miami?
Yeah,
So
so
that's
it's an interesting challenge from a communication standpoint because
yeah,
it's when you're actually trying to communicate it, more data is not necessarily easier to communicate, right?
yeah.
But if we move to a world where preparation and evacuations and so forth are all threshold oriented. And we can be convinced that these odds really do represent the real threat odds. Then it does make a preparation in some sense easier to trigger, right?
Yeah,
If
I think plots like the one you showed before with the colors on the different probability distributions, I
Mhm.
think those will be very, very helpful to start visualizing. Once the more ensemble members, I think your current system, because it aggregates multiple models, already has more than 100 members. So imagine if you had even more, you could start talking about low probability events. But still, because cyclones are so impactful, it really matters to have this nailed down.
Yeah, I always say the risk that something will happen is the odds that it will happen times the consequences. So if the consequences are
Exactly.
huge, but the odds are low, you can have significant risk. And, that's what we deal with when we talk about hurricanes hitting the coast and especially major metropolitan areas. All right, Jordan?
Next question coming in from our TikTok audience. And so a fun one here. Do you guys have like a nickname or a code name that you guys call the hurricane model? Like there's different ones out there like Sora from different companies, and everybody has like Chat GPT, and there's different ones. So the TikTok guys are wondering what's the secret name you guys have at Google when you're talking about the model?
Yes, so we have one that's close to ChatGPT in that it's quite complex. It's called FGN. It's a scientific name is Functional Generative Networks. But the moment we put it out to NHC and Bryan trusted testers, we started calling FNV3 because it was the third generation of this FGN technology
Mhm.
that we had developed internally. And then because the way that these cyclones are transmitted between agencies, you need a four-letter code name. So we couldn't put FGNV3, so we decided to call it FNV3. And so when we talk about the current model, we call it FNV3, and then when we call up the next model, we call it FNV4. But we realized that this is a complex name, and so we publicly and also to highlight that it's still an experimental model. And that it's kind of work in progress. That's we also decided to call it our experimental model for now. And then once we are fully confident after a season of tests, then we probably will give it a name.
Yeah, yeah. And my comment was, I don't know, FNV, those letters just don't roll off your tongue nicely,
Right, right.
right? So
So,
actually, the Hurricane Center calls it GDM for Google
yes,
DeepMind,
that's,
right?
that's
So the GDMI model is the early uh, Google model that they use to look at, for instance, for the 5 o'clock advisory or something
yeah.
like that. Okay, Jordan.
Yep, next question coming in. A little bit about seasonal forecasting. Can the upcoming hurricane season forecast for the number of storms expected to be generated using DeepMind? So we've talked about actual forecast tracks. What about seasonal forecast?
Have you undertaken a look at long-range forecasts?
That's a good question. So we've started to make some analysis, but for now, most of our analysis have been around the 2 weeks. So this mid-range weather forecasting. However, other AIs models, like for instance, there's a team at Google Research called Neural GCM that combines AI and physics, and they have tested that their model makes realistic predictions not about the location of the cyclone, but about the number of cyclones in this seasonal forecast. So it's there is quite a bit of promise on that front as well.
Yeah, and I think that this combination idea of using AI on top of the physics-based models is probably going to be something we'll see for a while anyway, right? So on the, a lot of the reaction I've initially got, and I must say less so now, but initially got was, every time I use ChatGPT, it gives me the wrong answer, it seems like. And so I say, okay, so just tell it you got the wrong answer, and then it's going to think harder, because that's the way they do it, right? Because they want to use the minimum amount of compute that they have to answer you. But I can tell you that ChatGPT or Claude, I use Claude a lot, and I'll tell it that was a really bad answer, and then it'll go off and it'll say, "Oh, I'm so sorry, you're so right. Let me think harder on that," and then it comes back with a really good answer, and if I understand right, it's because that they have a sort of a router in there that says use a little compute. We think we can answer with a little compute, and then it applies more compute if you tell it to. Anyway, I assume you don't have those kind of problems with Google DeepMind that
Well,
how much compute you need, right? I mean, this is a different.
yes,
What I'm trying to say is this is not ChatGPT that's made for a consumer service. So comparing the issues that you might have by asking it some kind of question is not the AI doesn't equal AI in this kind of
exactly.
situation.
So that one confusion I've seen sometimes reading stuff online, that we are not asking Gemini to give us the weather, where the weather is going.
Mm-hmm.
The very basic technology, some of it is shared with Gemini, in that we all use deep learning, neural networks, machine learning. These words apply to both. But our technology is quite tailored to weather. We only train on weather data, and so on. So, for instance, in language, you want to predict the next word at a time. It looks like a sequence. In our case, we have kind of a mesh around the Earth, and parts of the Earth also talk to other parts of the Earth. And so it really is quite tailored to weather. At the same time, we have trained, like the way we train the model is by saying, okay, predict tomorrow, and then we show it the mistakes it has said, and then try again. So we tell it to adapt its weights, and then it's a basically trial and error for thousands of times, hundreds of thousands of times, and then we tell it, okay, now this is the weather today. Please predict the future, and then after having made many mistakes, then hopefully it makes good predictions for the future.
Hundreds of thousands of times in the blink of an eye is what's the most amazing thing.
The training takes days.
The training takes a long time. Right.
Yes, the training takes a long time, but then the prediction, when it comes to real time, it's still quite expensive. I mean, compared to a Gemini query, because the Earth is so vast, the images are so high resolution. However, whereas millions of people talk with ChatGPT or Gemini, there is only kind of one weather for the entire Earth, right? So
Right.
we have one prediction. So because we only have one, it's very cheap. When you think about it globally.
And compared to the supercomputers that run for hours and hours
Yes,
to run a
exactly.
physics-based model, for sure. Okay, Jordan?
Next question coming in. Since the model is so fast, why not produce a forecast each hour instead of every 6 hours?
All right, Ferran?
That's a good question. So it's because depend on the European agency for what's called data assimilation. So they do data assimilation every 6 hours. That's also why a lot of global models, well, not just the Europeans, they also the other like GFS also I think does it every 6 hours. Other models do every 12 hours. So because we ingest the European agent data simulation as input, that's why we make forecast every 6 hours. It's true that going forward we could make predictions potentially if we were to ingest observations more frequently than every 6 hours.
So this data assimilation is really the unheralded critical part of making weather forecasts, and that is that you have to have a starting point, right? You have to know what the weather is at time zero, whenever that time zero is going to be. It's normally, if we talk Eastern time, 8 a.m. this time of year, or 8 p.m. or 2 a.m., 2 p.m. And you get all these observations, but they don't all happen at that time. And the European Center has, I guess, world-class, you would say, data assimilation where it looks at all this data. Some comes in at 7:30, some comes in at 8 or whatever. And it says, okay, we know how to adjust that to make a representative set of data for 8 a.m. as a starting point. So that takes, what's that take? A couple of hours, 2 or 3 hours for them to do that?
It takes more. It takes around 6 hours almost. Since
really?
Since the middle, it takes 3 hours after the assimilation window. But because they wait multiple hours to collect observations, and then after it finishes, then they keep making even more. More and more steps. Then a second reason to do it every 6 hours is also because NHC, the National Hurricane Center, and all these operational centers also operate around that cadence. So we really coordinated quite tightly this hurricane season to make the forecast exactly when the National Hurricane Center needs it. So they told us we want it by 6 hours 30, and then we have an amazing team of engineers that really put a lot of effort to get the forecast on time.
Yeah, but that whole data assimilation process is really important, because I can remember back in the day, I don't know whether it's still true today, if you took the European data assimilation and run the GFS model on it, you actually end up with very good results, which tells you that the model was actually quite good. But the data assimilation process is very hard and very computer intensive, and just takes a lot of computer power that the European Center deploys to that task. And I think pretty much everybody who's running an AI model these days runs it off the European Center data, or the ones that I know about anyway, because it is given to be the world-class data assimilation. Is there I mean, can you imagine ingesting all that data and sorting out all the things that the European Center goes through to actually get a starting point?
That's quite an endeavor because there is really tons of observations. There is also like an upside in the sense that machine learning is really good at kind of figuring out patterns in the data, and we know, for instance, there is some sources of satellites that we cannot assimilate using traditional physics that AI could unlock and be able to leverage the full potential of these observations. So it's a very complex challenge, but also there is a lot of upside if we were to solve it.
Yeah, it feels like something vast with a lot of different data points and a lot of things that have to be sorted out and thrown out and adjusted. It feels like an AI task to me, much easier than a brute force task that the European Center has to do. All right, Jordan.
All right, next question coming back in from Shane, another very good question. What goes into training, retraining the model? European releases ERA6 next year, so a huge improvement in resolution of the mechanics compared to V5.
So are you going to ingest that and retrain? You go through that whole process? Is that a yearly thing, or how often does the training process happen?
That's a good question. So we do retraining for two purposes. One is when we make a new, let's call it invention or a new model version, and then we want to see, is the model performing better or worse than without this potential improvement. And so we have a lot of that's kind of internal research that we do, and then when we made a lot of progress, then we put out a new version out. So every time you want to check whether an improvement is giving you, whether a change is giving you improvements, you have to retrain the model. And the second reason to retrain your model is is because you have extra data. So, for instance, if Iveta 6 comes out, we'll certainly leverage it to train it the new models. Another thing that happens is just time passes and you have extra data, and so usually we have seen that you need the most recent data to squeeze out all the full potential of ML. It's not like the model gets super bad, but it does get better and better the more recent data it has seen.
So does the model learn as it goes? Have you been able to detect that it's does better next week than it did last week because it just has seen more or gets smarter in some kind of fashion?
No. So what happens is we train the data until the end of a single year. So, for instance, the model that's running right now has been trained until the end of 2024. And then usually we evaluate it at the end on the following year. So we train a model until end of 2022, and then we evaluate it in 2023. We train one on 23, and then we evaluate it on 24. And so right now the one that's running is trained until the end of 2024. What you're alluding to is a thing in machine learning, but it's quite expensive. It's called continual learning. It could be done effectively, but there is a bit of research that would need to go on to have continually learning systems of the weather. But it's a very interesting idea.
But it's not an intrinsic to AI, is my point. Okay, all right.
No, exactly. It's not. Right now, the models are not learning on the job. Let's say they could do it, but right now, at least our model is not learning on the job.
All right, that's interesting. I thought that was just the way those things work. All right, Jordan.
Next question. Will you reveal something for winter forecasting?
Oh, interesting question. I just raised that question just the other day. All right, Farhan.
Yeah, I've seen your email. It's an interesting, it's an interesting challenge. For now, I don't think we have anything announced or planned for announcement on that front. We do have quite generic weather models, so our model is very good at cyclone forecasting, but it's good at other parts of the weather. So we are really interested in seeing what other potential applications. So Bryan mentioned the other day to us also.
Yeah. So great minds think alike. So because the winter problem for coastal locations is very much like the cyclone problem. It's very threshold oriented, right? It's very much where is the rain snow line going to be and how far inland. If you're talking about Washington, for example, you can have completely different weather on one side of the city than you have on the other side of the city. It's just very often because of the ocean impact and the temperatures. And so it is this kind of thresholdy kind of thing. Anyway, it'll be interesting. It feels like an AI kind of problem to me to solve for the future, for sure. Jordan?
Hi, so our next question coming in from our TikTok audience, somewhat related to winter forecasting, but not quite. They're wondering if you plan to expand the number of members in the ensemble. We talked about 50 earlier. Why not go higher?
Yeah, why not? No, I think Farhan said that they're thinking about going higher. So
there is one reason, which is a bit funny.
Okay, go ahead.
To interrupt, but just to give one bad news, which is the weather data is surprisingly big. Like there's a lot of data. If we think about it, it's just a single variable. Let's say the temperature at 2 meters. It's like a very high resolution image. Then you have a video of it, right? Because we're predicting it in the future. Then we have hundreds of variables because we also have different layers of the atmosphere. So really, one forecast is really huge. And if we want to store 1,000 forecasts for a single year, then it starts to be big. Even at Google scale, we are biggest consumers of disk space. So that's one thing that also we have to think about.
Yeah, and is there just from a science and a statistics standpoint, it would seem like there is a diminishing returns number, right? Do you know from research, like how many ensemble members do you have to have before it's not worth having more if you could have an unlimited number?
That's a good question. So Ilan, one of the research scientists at our team, has looked into it. Still preliminary research, but There is some variables or some measurements for which you do have diminishing returns. We'll have to see exactly where, because they could be beyond 50. But there's some other variables that you see a lot of progress even with bigger ensembles. The reason being what you were saying before about kind of probability times risk, or risk times consequences, which is if there's really lots of consequences, then and you care about these 1% probabilities, then really having 1,000-member ensembles allows you to quantify them a lot better.
Yeah, it depends
And so
on the quantity, I
there
guess,
you
that
have
you're
massive gains from large ensembles.
right. It's high consequence events. Yeah, I can
Yeah.
see that. All right, Jordan.
Not very many more questions left. Maybe you guys just want to talk a little bit about what's next. You kind of tried to hit on it earlier, what you guys are planning to do, upgrades in the model. But what are you guys thinking in the next 6 months, 1 year, 2 years, 3 years? What's the future look like?
Well, so Ferran, we didn't explicitly say, but I know that in the middle of Imelda, you released an update to the model, and we talked before we started here, and you said that you didn't think that was why that they got much more certain that it was going to turn right. That it was just more likely just the timing. But in any case, what prompted the upgrade? Are there things about it that people should know, should understand as they look at what they can see on Weather Lab right now?
Yes, that's a good question. So we did release a minor update. We call it tracker only because the neural network stayed the same, but we have a light tracker on top of it, and we did make some improvements to it. Some of them came from feedback from trusted testers like you, but also weather agencies. We talk with UK Met, we talk with Australia, with Japan, and we especially talk with the National Hurricane Center and forecasters there. And we received a couple of feedbacks from the beginning of the season. One is that our tracker was making jumps. So the neural network predictions were perfectly fine, but the tracker we had implemented ourselves was making mistakes.
So the tracker, just to be clear, the tracker is the thing that makes those lines that you see.
Yes,
on
just stitching the points, literally
Right.
stitching the points.
Right. It's connecting 2 points that should not have been connected.
Yes, exactly. So that was not working well.
Yeah.
And then the other thing that the forecasters asked us is for members to be realistic. So sometimes there was a few physical inconsistencies, not a ton, to be honest, but a few. For instance, predicting negative radii in some rare cases, and we wanted to fix that. And so we really coordinate quite closely with the National Hurricane Center, so we wanted to be maximally useful to them, and so that's another thing that as we saw the 2 hurricanes that were approaching the East Coast, we said, okay, we better deploy them now. So we rushed. A few of us rushed to deploy this model.
So is it something equivalent to what, if you really are doing a project with Claude or ChatGPT or something like that, that you put some more in the prompt to tell it to quit doing that thing? Is it a process analogous to that at all, or is it something completely different?
No. In this case, it looks like regular software engineering of like Python code, just touching different parts of regular Python code. Usually, essentially there is no concept of prompt in our case. The prompt is really the weather of today, and maybe some other information on what time of the year it is and things like this. But we don't speak English. Our model doesn't speak any language. If sometimes we have seen, okay, maybe we need to train our model differently, or we pre-process the data differently, so that can happen.
So the pre-processing process that's sort of a secret sauce of taking in the data and getting it, designing the data or molding it so that the model knows what to expect and what to do with it. Is that fair?
Yeah. So there is a bit of science in there. So you do have to know math and physics enough to think what might be useful to the model. So, for instance, an example of this is that the model ingests things that are not even in the same units, right? It has wind pressure in hectopascals, it has temperature in Kelvin, it has wind in meters per second. So it really has to make sense of all of this, and we have to first normalize all the data so that the model can kind of even talk about numbers of the same scale in order to learn meaningful patterns from it.
Yeah. Okay. All right, Ferran, we're going to let you go because I know we're keeping you up late, and we really appreciate your time here. And I know everybody benefited from this to understand what they're looking at and what they're hearing about, because we have heard a lot about the Google DeepMind model this hurricane season, in spite of the fact of being a quiet hurricane season, relatively speaking. Imagine if it had been busy. Anyway, this is so much good news and good information, and it's been a pleasure having you on, and thanks so much for your time.
Thanks. Thank you. Pleasure being here.
All right. So just Google Weather Lab if you want to, play with it, look at it. You can also go, by the way, to weathernerds.org. It turns out, just for reasons related to the timing of the data coming out of the European Center, the Google data shows up on Weather Labs or weathernerds.org a little earlier, and some other sites as well. So anyway, but we certainly appreciate everything that we get from the work they've done with Google DeepMind's model this year. And we have used it in combination with the European and GFS, and I think to very good benefit here at Fox Weather. All right, thanks everybody, and stay in touch with us. We'll see what happens here next week with this system moving off of Africa. And of course, we'll see you on Fox Weather, and we'll see you right here online as well. You have a good evening. Take care.